I'm Mark Kavanaugh for Cavi Coaches, and today I'm going to coach you up on centripetal force and how that's related to centripetal acceleration. In this video, we're going to talk about centripetal acceleration and centripetal force and how they're related to each other. So let's first review the motion map properties. A velocity vector at any given point is subjected to an acceleration that turns it but does not speed it up or slow it down. The acceleration vector is always at a right angle to the velocity, and the acceleration points toward the center of the circle, and the velocity is drawn tangent to that circular path. So the equation for centripetal acceleration is that AC is equal to v squared divided by r, where AC is the centripetal acceleration in meters per second squared, v is the tangential speed, meaning it's tangent to the circular path in meters per second, and r is the radius in meters. And we can see a diagram of a motion map where velocity is at a right angle to the acceleration, and acceleration points towards the center. This is important because now when we transition to centripetal force, which is what we're going to talk about now, it's important to know that the acceleration is directed towards the center. And that force that's responsible for uniform circular motion is called a centripetal force. If you remember, we use the Latin centri and pedal to translate centripetal to be center-seeking or center-directed force in this case. In the previous video, we talked about a centripetal acceleration and broke that word down. So centripetal, just remember, means center-seeking or center-directed. Now, centripetal force is simply Newton's second law, mass times acceleration. So centripetal force is equal to mass times centripetal acceleration. Now, you may have heard this phrase, centrifugal force. A centrifugal force is actually, it's just a myth. It was believed that when you were turning, that feeling of you being pushed towards the outside of that turn was a force, and they called that the centrifugal force. But what we know is that it's not a force at all. It's just our body resisting that change in direction and wanting to go in a straight line. So we need to think about Newton's laws and system schema to be able to draw free body diagrams, which we'll look at here in just a minute. So centripetal force is Fc, and we know that centripetal acceleration is v squared over r, so we can substitute in, knowing that centripetal force is in newtons, speed in meters per second, r is the radius in meters, and mass is m, of course, in kilograms. And looking at this same diagram, but changing that to centripetal force, the centripetal force actually points towards the center as well, and is also perpendicular to the speed at any given point. So is this reason why centripetal force can do no work is because centripetal force is perpendicular to the speed. The centripetal force can alter the direction of this object without altering the speed. Now, if we know the speed doesn't change, that means kinetic energy remains constant. That means work is zero using our work energy. No change in kinetic energy means no work that's done. And we know that using the equation, FD cosine theta, if they're perpendicular, theta is 90, and if theta is 90, that means cosine of 90 is 0, so there's no work that's done. Now, centripetal force is not a unique type of force. This force arises from other forces that we already know, a friction force, a gravitational force, a tension force, a normal force. They can all provide a centripetal force as examples. So there's no force you're going to draw on a free body diagram and label it as centripetal force. It's just going to be a force that is already known, which is important when drawing our system schema. We know that drawing a free body diagram is not going to be any different than what we've done based on our system schema. You can always identify the real force which is causing the centripetal acceleration, and that's going to come from your system schema. And looking at your free body diagram, there's an unbalanced force pointing towards the center of a turn. And nearly any kind of force can act as a centripetal force. Friction is a centripetal force. If you're driving in your car and you're making a turn, as this guy is in his car, making a right-hand turn, we're looking at a head-on view. If he was on ice, he'd make the turn and he would go straight. But in this case, he's not. So there's friction on the road. So we're looking at a system schema. We have the road supplies friction and normal force, and the earth supplies gravity. So we draw our free body diagram. We're going to draw the x-axis and y-axis. We know the normal force and gravity point in the directions they do, and because he's turning to the right, from our vantage point, which would be left, the friction force is going to point to the left. Now, just like any other situation, you'd write your second law equation. Adding up the forces in the x direction equals mass times acceleration. The friction force, in this case, is the unbalanced force, and that's going to equal mass times centripetal acceleration, and we know centripetal acceleration is v squared divided by r. Now, don't stop there. We're going to look at our equation in the y direction as well. And in the y direction, there is no acceleration, which means that the amount pointing up equals the amount pointing down, so normal force is equal to the gravitational force. Fn equals mg. Now, at this point, you might need a third equation to write the friction equation. Friction force equals mu times the normal force, and now you have a system of equations, and you've built the framework for your problem solving, and you can substitute values in for each of those equations. Now, we can also use the normal force as a centripetal force. So when we're talking about a car, a NASCAR or an Indy car, going around a banked turn. So we draw our system schema, and we're going to make this simple and just say that the road is frictionless going around that bank turn, and that the road is only supplying a normal force, and gravity is being supplied by the earth. Now, if you remember back when we learned to draw free body diagrams, we discussed that the x-axis is always drawn parallel to the surface. That is not true in this case. On banked roads, you're going to draw the x-axis horizontal and the y-axis vertical. In our free body diagram, the normal force is still going to point perpendicular to the surface, and gravity is going to point to the center of the earth, which is down, and we have our free body diagram with the normal force up and gravity down, but the normal force is at an angle. And remember, the x-axis does not get drawn parallel to the surface for banked turns. So we make this our working free body diagram by drawing our vector components. We have an upward component and a rightward component and theta. If you draw your angle this way and your components this way, as pictured on the screen, that tells us that the angle theta, that's going to be the angle of incline for the bank turn from the horizontal, which is most cases what you're being asked for. So now we label those vector components with our trig functions, and now we're going to write our second law equation for both directions again. So in the x direction, we only have one force pointing towards the right, and that's Fn sine theta, and that equals mass times centripetal acceleration, which is v squared over r. So we end up with our equation of Fn equals sine theta mv squared over r. In the y direction, again, no acceleration, so the upward force, Fn cosine theta, equals our downward force of mg. Now at this point, we might not be able to find the normal force, so we can solve our y direction equation for normal force in terms of mg and theta, and substitute that back into the normal force in our x direction equation, giving us an mg over cosine theta times sine theta on the left side of our equation. So let's look at an example of a pendulum that uses centripetal force from a combination of tension and gravity. So as it swings back and forth, the point we're going to look at is when the pendulum is straight up and down. So we're going to draw our system schema. We only have two forces, a tension force and gravity. The tension force pulls up on the pendulum and gravity pulls down. Now, because it's in a circular path, we know that at the bottom, it's accelerating towards the center, so the upward force is going to be greater than the downward force. So we write our second law equation. Tension minus gravity is going to equal mass times v squared over the radius. So at this point, we know that anytime an object is moving in a circular path, the force directed towards the center is going to be bigger than a force that is directed away from the center, which is why the tension force is greater than the force of gravity in the case of a pendulum swinging back and forth. So let's look at an example of a roller coaster. This is one from Carowinds, which is a place that I take my students each year at the end of the school year. And a centripetal force arises when you're upside down from a combination of the normal force and gravity. Now the key here is you're upside down. You're at the top of the loop of that Carolina Cobra. When you're upside down, that means we still have a normal force and gravitational force, but the question is, which way does the normal force push? Well, if you're upside down, the normal force pushes downward, and gravity also points downward. Now, when drawing free body diagrams, you're going to be asked to draw a distinct vector for each individual force. So when you draw that, that means you're going to have to start each vector on the dot and draw away. So if you have two forces acting in the same direction, you're going to have to draw them next to each other. Don't draw one force and one vector and label it two things, or draw them added to each other. Draw two distinct vectors starting on the dot. So mg and Fn work together. That's important for when we write our second law equation. We know it's only forces in the y direction. Now they work together, so that means we're going to add them. Fn plus mg is going to equal m times the centripetal acceleration. Then we change centripetal acceleration to v squared over r. So we have our equation for our normal force. Fn plus mg equals mv squared divided by r. So this is how you use centripetal force and drawing free body diagrams to derive expressions. I hope you have a great day and an even better tomorrow.
If you found this video helpful, don't forget to click the like button down below and subscribe to my channel, Cavi Coaches, and follow me on Instagram and Twitter @CaviCoaches.